So we talked about these two interpretations of probability. Relative frequency, which is what we're used to, okay? I can flip a coin 10 times and count how many heads, how many tails. And then the personal probability, which is, again, more of an estimate as to what you think your chances are of an event that, I mean, that event could be personal to you, but it's something that cannot be repeated and fit this relative frequency definition. Now, we saw when we were talking about personal probability that that's definitely subject to different psychological influences. We have trouble being able to process the likelihoods and the outcomes of different events. Now, relative frequency, because it can be measured, does that mean that it's a little bit more accurate, or we have a better understanding as human beings? Yes and no. Sometimes that's true, but a lot of times that's not. And we're really bad with improbable events. Improbable does not mean impossible. And it's that right there that leads us to believe that coincidences shouldn't happen. Okay? It says, are coincidences improbable? Well, we had two researchers that kind of gave us a definition of a coincidence. It says, a coincidence is a surprising concurrence of events perceived as meaningfully related with no apparent causal connection. So there's no reason why these two unlikely things should happen, but they happened. That's essentially what a coincidence is. They're meaningfully related somehow, they're connected somehow, but it's incredibly unlikely that it happened. Now, I mentioned this example last week when talking about things that seem improbable. Winning the lottery is unlikely, but winning the lottery twice seems like one of these things that you'd get struck by lightning. Okay? It's that sort of unlikeliness. But it's happened. I'm not talking like little scratch-off tickets, but multi-million-dollar jackpots. It's happened to this woman, Evelyn Marie Adams, in 1986. She won the New Jersey lottery twice in a short period of time. The New York Times said that the odds of one person winning the top prize were about 1 in 17 trillion. And again, if we have trouble interpreting small probabilities, we have a problem interpreting large numbers and how big 17 trillion is. Okay, 17, 1, 2, 3, 1, 2, 3. We're at million right now, billion, trillion. Okay, that's incredibly unlikely to happen, but it happened to her. It happened to other people. It happened to Robert Humphreys. He won the Pennsylvania state lottery twice. Total winnings of $6.8 million. Now, there are other situations that are like a little bit more perceivable to us than winning the lottery. The author of this book, this is my old textbook before this class was like CHS statistics, and the author of this book says, when I was in college in upstate New York, I visited Disney World in Florida during summer break. While there, I ran into 3 people I knew from college, none of whom were there together. A few years later, I visited the top of the Empire State Building in New York City and ran into 2 friends who were there together and 2 additional unrelated acquaintances. Years later, I was traveling from London to Stockholm and ran into a friend at the airport in London while waiting for the flight. Not only did the friend turn out to be taking the same flight, but we had been assigned adjacent seats. And you always hear stories similar to that, where I was on vacation and I saw somebody that I knew from back home while I was away on vacation. And that satisfies this definition of a coincidence. It's a surprising concurrence of events. Okay? You didn't know that you're going to be in that same place at the same time. Okay? But there's a connection. You know each other from back home. But there's no apparent causal connection. There's no reason why you are both there at the same time. But I've said that probability sometimes depends on how you perceive it. And what the author was talking about here, Disney World, the Empire State Building, the airport in London, these are all big tourist attractions that a lot of people go through these places every day, every month, every year. And it's not like you went there saying that, boy, it sure would be rare or strange or bizarre if I were to see this person at this time in this place. Instead, you're saying, I happen to bump into this person that I know. I'm not really close with this person, but I know of them. I recognize them. They recognize me. What a coincidence. You usually say something like, oh, what a small world. Everybody has a story like that. And if you flip around the perspective, again, it's not like you're pre-identifying this individual, but instead, it's somebody that you met somewhere, sometime. I mean, we've met and would recognize probably thousands of people in our lives. For us to happen to bump into one of those people, okay, not at a predetermined time and location, but at a location that we did not expect. It's a major tourist destination if you're talking like Disney World or New York City or a major European airport. Maybe that likelihood isn't quite as improbable as you would initially think. Same kind of thing with these lottery stories. Okay? What's not improbable is that someone, somewhere, someday will experience those events or something similar. And that 1 in 17 trillion that the New York Times calculated, that was the probability that a specific individual would play the lottery, win it, play again this next time, and win it again. Yes, that is incredibly unlikely. But for, what's her name? Evelyn Marie Adams? Okay, I don't know who she is. For it to happen to somebody, somewhere, sometime, I'm opening it up to all of the people who play the lottery. And I'm not saying it has to happen now. That was back in 1986, almost 40 years ago. Okay? And it's happened a few times over the span of the last few decades. Okay? Millions of people play the lottery every day. So it's not as surprising that someone, somewhere, someday would win it twice. And as I said, a couple other people have had that event happen to them, where they've won it twice. And these two researchers calculated that there's at least a 1 in 30 chance of a double lottery winner in a 4-month period. And if you take it out even further, look at the big picture. It becomes more likely than not that there would be a double winner somewhere in the United States in a 7-year period of time. And how's that for a flip of events? In that if you take it out long enough, this incredibly rare thing, if you go too long and it hasn't happened, then it becomes surprising that it hasn't happened. Again, you always go back to like a rare event, getting struck by lightning. Well, if nobody was struck by lightning for the longest period of time, that's pretty rare. Okay? Same thing with double lottery winners. It depends on the perspective from which you are viewing it. So, coincidences only seem improbable if we ask the probability of a specific event occurring at that time to us. Now, don't misinterpret what I'm saying. Yes, if you were to go out and play the Powerball tonight, and then you say, that $400 million, that's just not enough. I'm going to play again next time, and I plan on winning it again. There, you're getting into those, that's even worse than 1 in 17 trillion type of odds. Okay? Because you're predicting that it will happen to this person, yourself, at this time. But if you were to open it up to anybody, anywhere, anytime, okay? Now, again, if you're saying win the Powerball twice, now you're adding specificity to it that is lowering that likelihood. But if you're saying any lottery, anywhere, may not have to be the big granddaddy of them all, but yeah, that's when these things do happen. They do occur. Okay? The multitude of experiences we have each day, it's not surprising that some of them may appear to be improbable or unlikely. Okay? Strange things happen, and that's mathematically expected. Okay? If we're to flip a fair coin 6 times, which of these would be most likely? All 6 as heads? Heads, heads, tails, heads, tails, heads? Or heads, 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 tails, tails, tails? Anybody have a thought? Which of these sequences is most likely?
All the same.
They're all the same. Why?
Because it's probability. Technically.
Yeah? What do you mean? It's probability.
It's impossible to get it to be like, I don't know how to explain it.
Let's say you flip the coin that first time.
Yeah.
Does that impact the probability of that second flip being a head or a tail?
Well, for the order, wouldn't it? If you wanted it to be like heads, heads, tails, heads. If you got a tails, it can't be heads, heads, tails, heads.
Yeah, but that's still one of the possible outcomes when you're flipping a coin 6 times, right? This nothing but heads, is that more or less or equally likely as this one? Equal. And how about this one?
They're all equal, right?
They're all equal, yes. Which a lot of people don't see it that way. Okay? They don't like this. They don't like this because it doesn't appear to be, again, misunderstanding of what random means, but they don't think that this appears to be random. They think that this one is the most likely outcome because it has that appearance of randomness. No. They're all equally likely if you were to look at everything that's possible. Go back to Kahneman and Tversky, Kahneman and Tversky, and misspoke, that we talked about them and their research in the psychological influences section. And people think that a long-run frequency of an event should apply even in the short term. That is the gambler's fallacy. You think that there's a memory that, boy, I've come up heads a lot. That coin, it better come up tails. I'm due for a tails. Okay? People believe that even small samples are highly representative of the populations from which they are drawn. In considering tosses of a coin for heads and tails, people regard the sequence heads, tails, tails, heads to be more likely than the sequence heads, 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 tails, 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 which does not appear to be random, and also more likely than heads, 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 tails, heads, which does not represent the fairness of the coin. But in the long term, in the big picture, it's expected for us to get 4 in a row. It happens. In the big picture, it's expected for somebody to win the lottery somewhere, sometime. I'm not saying that I'm going to flip a coin now and get 4 heads in a row. That's like borderline winning the lottery, right? Not that rare, but it's the same kind of thing. If I'm flipping a coin 500 times, over those 500 flips, you're going to see 4 heads in a row, 5 heads in a row. Okay? Maybe some streak that would be unexpected to say it's going to happen now. But to look at the big picture and, I got this sequence of 6 in a row. That's not unlikely. Independent chance events have no memory. You'll hear people say this, well, it's the law of averages. Okay? It's regression to the mean if they really want to sound like astute. We talked about regression to the mean, linear regression. Okay? The law of averages, there is no such thing. People tend to believe that a string of good luck will follow a string of bad luck in a casino. Okay? However, making 10 bad gambles in a row doesn't change the probability that the next gamble will also be bad. Okay? You look at like recovering gambling or gambling addicts, like stuff like that. They say like, don't chase lost money. Okay? Don't think that I've had a real bad string of bad luck. Okay? But it can't get any worse for me. Okay? I'm due to have it turn in my favor. No. Okay? 10 bad gambles in a row doesn't change the likelihood that the next gamble will also be bad. These are independent events. Okay? Probably seen this guy before, Penn Jillette. Luck is statistics taken personally. That's a pretty powerful quote there. If you think good luck or bad luck, believing in luck, that's a very personal thing too. It's almost become everyday and almost mundane for us to, oh, you have a test today, good luck. Okay? You just do it. We don't think much about it, but can you do things to change your luck? Is luck a thing? You're just carrying around that like dead rabbit's foot on your keychain, like some people believe that brings them good luck. Does that do anything? Does walking under this open ladder, does that decrease your luck? No. Luck is statistics taken personally. You're putting a personal spin on that. You think, oh, whatever I do here, that's going to influence or impact other things that are totally unrelated to one another. They're totally independent. So this gambler's fallacy. The big thing here is that it applies to independent events. And it may not apply to situations where knowledge of one outcome affects probabilities of the next. So when you're talking about like casino games, like the roulette wheel, where the ball spins around on the wheel and you bet money on a number or a color or something, and if it lands on that, that's independent. Each spin is independent. But other games like blackjack, where there's a deck of cards and there's a known sequence of events that can happen and you can keep track of that, those are no longer independent. And people will say that blackjack is the game where the player has the best chance at getting those odds close to 50-50. And every other game, the odds are steeply in favor of the casino. So card games using a single deck. Knowledge of what cards have already been played provides information about what cards are likely to be played next. Talking about card counting. Confusion of the inverse. This is the idea here that a lot of people who should know better really screw up. And it causes a lot of anxiety because of that screw up. Let's give a hypothetical here. Let's say that a patient they detect a lump. And they go to the doctor because they want to get it checked on. And the doctor says that, well, I'm not too concerned. I think there's only a 1% chance that it is malignant, okay, that it's actually cancerous. Well, a mammogram, if we're talking about breast cancer here, it's 80% accurate for malignant lumps, meaning that 80% of the time when it's actually malignant, that it will come back as malignant. It's 90% accurate for benign lumps, meaning that if it's not cancerous, it's going to come back and say that it's not cancerous 90% of the time. So, they run the test, they perform the mammogram, it comes back and says that it is malignant. What are the chances that it is truly malignant? Now, in a study, most doctors said about a 75% chance. They recognized that there was some margin of error, some impreciseness to these tests, but it's really only about a 7.5% chance. And the reason here is a misunderstanding or a confusion of conditional probability and a confusion of the inverse. The doctors were confusing the probability of cancer given a positive mammogram, confusing that with the probability of a positive mammogram given that the patient has cancer. We've seen with conditional probability that when you switch the conditions, the likelihood changes. And the doctors are messing this up. Now, just over the last year, a lot of this has changed. Okay, I was teaching this lesson last year and looking at COVID testing, and you're talking about an imprecise test with something that has a chance of going wrong. It's imprecise and it's relatively rare with everyone who is taking the test, that you're going to get a bunch of false negatives and a bunch of false positives. One way to look at this is lay it out on the table that we've been working with. So let's make a hypothetical table here for 100,000 women with this lump and the prior probability. Remember, the doctor initially said there's only a 1% chance that it's going to be malignant. Okay? So the test comes back that it's malignant. So we have our 100,000 women. 1% of that is 1,000, where it's actually malignant. The other 99,000, the lump is benign. Now, when you go back and look at those numbers, mammograms are 80% accurate for malignant lumps. So, if it's actually malignant, 80% of the time, the test is going to say that it's malignant. It's a conditional probability. Of those 1,000 where it's actually malignant, 800 of them, the test says it's malignant, 80%. And we said that the test was 90% accurate for benign lumps. So of these 99,000 where it's actually benign, 90% of them, the test is going to say it's benign. 89,100. And we have the complements over there and over there. So you fill in the rest of the chart, just like we did in our homework. Add the totals. Check that it gets up to 100,000. So our question was saying this woman comes back and takes the test and it comes back as malignant. The probability that it is actually malignant, okay, she is in this category, where the test shows that it's malignant. The probability that it's actually malignant is only 800 out of these 10,700 where the test showed that it was malignant. 800 divided by 10,700. Where's that 7.5%? It's a confusion of the inverse. And people are thinking that It's a higher likelihood than it actually is. It's a misunderstanding of conditional probability. All right, so I wanted to wrap up with that kind of extension here. People have a poor understanding of probabilities that are unlikely, but unlikely events do happen. Okay. Any questions on this?